Hi, welcome everyone. And I'd like to start with the usual, which is thanking the organizer for giving me an opportunity to speak. And with this opportunity, I would like to talk about what are lucky droplets in air turbulence. Before going into the results, however, I would like to motivate why Rama and I are interested in this problem. And it all deals with cloud droplets in air. So when you see a cloud, which is something like this hanging over ICTS, these span kilometers, but they are made up of water vapor which form cloud droplets that eventually rain. And there is a large scale of lengths that is involved from converting vapor to rain droplets, which ranges around order of millimeters. There's even a larger scale of lengths that spans from millimeters to order of kilometers that make up the whole cloud. But today we'll be focusing on this range of scales where water goes from vapor in its gas phase to rain droplets, which is around 1 millimeter. And there are two barriers in these scales of lengths which are interesting. One is this 2 and 10 micrometer, and another is 50 and 100 micrometer. So if the water droplets are less than 2 and 10 micrometer, they grow by condensation. The water droplet forms, and the water vapor aggregates on its surface, and it grows. But after this diameter, the condensation rates slow down, and the water droplets cannot grow further any faster. On the other hand, if the water droplets grow beyond 50 to 100 micrometer, it starts falling under gravity. And while it falls, it collects all the other droplets on its way, grows, and becomes the rain. But in between this 10 to 50 micrometer, neither of these two phenomena is fast enough for water droplets to grow. So the question is, how do they go from 2 to 10 micrometers to 50 to 100 micrometers? And the guess of physicists and engineers for the last 20 years is that maybe turbulence has a role to play. Turbulence maybe make them collide against each other and make them grow. Eventually, they reach this 50 to 100 micrometer and they start falling in gravity. Which brings me nicely to how cloud droplets behave in turbulence. And this, again, also depends on size. So if you have tiny droplets, they almost hug the streamlines you. As they grow a little bit bigger, their inertia kicks in. They gain more freedom to deviate from the streamlines. And once they grow big enough, they don't care about the fluid at all. They just start falling under gravity. And the non-dimensional number that captures is the Stokes number, which is proportional to the square of the diameter of the droplets. And like I said, for very small Stokes number, these particles hugs the streamlines. This is less than 10 micrometer. They don't collide much. If Stokes number is order 1 and above, they start falling under gravity. And in between are what's called lucky droplets. These experience drag, but they also have their own freedom to detach from the streamlines and collide with others. And we would like to understand the dynamics of these lucky droplets. But still, it's difficult. Why? A meter cube of cloud will have around 1 billion of particles. This desk captures a volume of meter cube, and we can't capture individual particles even in this meter cube of cloud. So this number is too many to simulate. However, this number is also dilute. In other words, if you compute the volume fraction in these water droplets, there will be 10 to the power minus 3 to 10 to the power minus 4. So the motion of these droplets really affects the cloud. So the idea is as follows. You have a few of these lucky droplets and many of these small droplets, and these lucky droplets sweep around these small droplets, collecting these small droplets in turbulence, growing, forming these big droplets, and falling under gravity. And how do we capture these if we can't simulate individual droplets? The answer is, of course, a reduced model. So remember, we want to simulate many small Stokes particles, few larger Stokes particles, and naturally, we can consider a continuum of the small Stokes, a sea of the small particles, and simulate their number density and velocity fields. Both of these are fields, while consider few of these individual particles, which is tractable numerically, and evolve their mass and velocities. Now, once we have this framework, we can derive equations for both of these cases. For the small particles, the velocity field will hug the background velocity u with small correction in the orders of Stokes number, and the number density will follow a continuity equation, except some of them will get eaten by these big droplets, which is the sink term in red. For the big particles, they will always collide and grow, and their growth rate will be given by the collision cross-section between big and small droplets, which depends on the dimension of the problem, and the local number density that the big droplet sees around itself, and the relative velocity between big and small droplets. If both of them are going at the same pace, they won't collide. Their velocities will also be augmented. So if these collisions conserve the momentum. If I'm a lucky droplet, I collide with a small droplet, then I get the momentum of these small droplets as I grow bigger, and that's the second term there. Interestingly, for those of you who are from fluid dynamic background, empirically you can derive that this follows a law like this, which is like sort of a nonlinear drag. Usually it's used in fluid dynamics in other contexts, but you can derive a nonlinear drag in this way. Okay, so what does the effect of this model looks like? But before going that, I must emphasize one point, that in this model, you don't have to evolve individual particles, look around all the other particles and see which of them have collided with each other. These small droplets will never collide, except with the bigger droplets, and the bigger droplets will always collide with the small droplets. You don't have to search for collisions in any of the algorithms. So how does this model look? It's easy to visualize in 3D, and it looks something like this. On the left, you have the vorticity field where the flow goes around in cyclones and anticyclones, clockwise and counterclockwise. And the number density of these small droplets looks something like this. They spread out of these high vortical regions, live on the edge of their vorticities, and then they move around with the vortices. And what the big droplets do in this exaggerated schematic is that they eat these small droplets and grow bigger. Now, this is an exaggeration, of course. Even though I'm calling them big droplets, in this picture, all the big droplets would be less than a pixel. So, but you can't see the contribution of the big droplets in the number density of small droplets. But if you put enough big droplets, you see the contribution. So let's say you put 10,000 big droplets, they eat up all the small droplets number density in between of these vertical regions. Okay, so now that we have the model, we can ask a lot of questions. One of them is like, is there an optimum location for these lucky droplets to start so that they grow faster? For this talk, I'll focus on something else. Is there an optimum size of these lucky droplets so that they grow faster? What do I mean by that? So if you have 8 10 micrometer droplets versus 120 micrometer particles, both of them have the same mass. And the question is, which one grows faster? If you do a naive kinetic theory guess, you'll find that the growth rate scales negatively with Stokes number in both 2D and 3D, which means this guess tells you 8 10 micrometer particles will grow faster than 120 micrometer particles. We want to test that in our model because our model have turbulence and all these interactions. So we kept the small Stokes number constant, varied the Stokes number of big particles in different realizations, and studied the growth. And the answer is sort of anticlimactic. So here you see the growth rate of these big droplets over time, and you see there is a monotonic decrease in the growth rate as you increase the Stokes number. The red grows the least and the yellow grows the most. And in the other two falls in between. This matches with the guess that we have qualitatively, not quantitatively. But because we have a model, we can comment on something more. We can comment that the initial growth will be something like a power law, and they will saturate later on with an exponential decay. And this is also seen in 3D, where you see when you increase the Stokes number of initial big particles, the growth rate decreases with this Stokes number. So this brings me to somewhat to the end of the talk, which is, I told you that we derived a simplified theory for lucky droplet growth where you don't have to look for individual collisions. We asked, does the size of these lucky droplets matter in their growth? Yes, if you put more smaller lucky droplets versus less bigger lucky droplets, you see better growth. And now what we are seeing is that these growth qualitatively matches with kinetic theory guess. So one may ask why turbulence is needed. I am doing these expensive simulations, but are they needed if I can guess the outcome with some kinetic theory guess? And this is the thing that we are thinking about recently. Is turbulent more important or polydispersity? So polydispersity was when you have a single size droplets and few slightly different size droplets. Is turbulence needed in this case, or will these polydispersed particles grow on itself? I don't have a concrete answer to that today, but meanwhile, I'll take any questions you may have. And thank you for listening.
Thank you, Rajarshi. What was the sigma IBS parameter?
It's the collision cross-section that we study in kinetic theories. It's between the big and the small droplets. And I is just for the I particle, because different big droplets as they start to evolve will have different masses depending on their growth rate. So this in 2D is sum of the radius of the big and small droplets. In 3D, it's pi times sum of the radius square. It's the collision cross-section.
Okay, and in the second term, there's a modulus in the first velocity difference,
Right.
but not a modulus there.
Right, because the outcome has to be a vector in the end, because we're writing acceleration. Yeah.
Hello.
You're using Stokes number here, right?
Sorry, yeah.
Stokes number, what is the ratio of the, what are the timescales you take?
So the fluid timescale is always Kolmogorov timescale. And in that case, for 2D, we started with small Stokes number of around, let's say, small Stokes number of around 10 to the power 2 into 10 to the power minus 3. And big Stokes number, we varied. Initial big Stokes number went up to 50 times. And 3D is almost the same.
So I have an idea like what Stokes number I think is a ratio of some two timescales in the problem, right?
Stokes number is the ratio of two timescale. One is the particle relaxation timescale, how fast it reaches terminal velocity, versus how fast the fluid is moving. Yeah, like fluid is evolving.
And what is the Reynolds number?
It depends on different cases. For 2D, the Reynolds number, we could go much higher. It's around, the Taylor Reynolds number is not well defined in 2D, but the actual Reynolds number will be around 10 to the power 5. But in 3D, the Taylor Reynolds number will be around 100 to 120.
Yeah, hi. Rajarshi, thanks for the nice talk. I'd like to understand, when you give the turbulence over there, is there like a preferential sort of eating of all these droplets inside the vortex or something like that? There is any specific locations in the turbulence?
That's a different question we are trying to ask. So what you see from this snapshot is that if you don't have any lucky droplets, let's see, come here, these are these vortex cores that the small particles centrifuge out, right? So most of these eating out won't happen in vortex cores, but it turns out if you start the big particles in these vortex core, it will centrifuge out faster, and with time it will eat more of the small droplets. That's a different question we looked at as well. Yeah.
Okay. Also, is there any time scale that one needs to meet in this? For example, the formation of rain and so on. Like, is there any time scale that you have to meet in your model?
Yeah, right. In the model, we haven't looked at the time scale it takes usually, but in atmosphere, it has to grow in matter of half an hour or let's say hour, because otherwise the sun will evaporate these droplets. That's also there, which is not there in the model. So ideally the model should capture growth in some fixed amount of time. Yeah.
Okay.
Hello, can I ask
Can
a
you
question?
give an idea about this kinetic theory guess that you give? Yeah.
So it's not you assume there are uniform small droplets around, and the number density decreases with the cube of the radius, and the collision cross section increases with the d minus, like in 3D it increases with the square of the radius. So you multiply that and you get the scaling. That's all. Yeah, thanks.
Yeah, can you go to the movie? I think you told me that in the slide that you don't need to worry about the collisions. So I think that these particles are, I think, overlapping sometimes.
These are exaggerated. Like I said, in actual reality, even the big particles will be less than a pixel here. And the volume fraction of these big particles are so less that we can ignore collisions at late time.
So in your 3D simulations also, these particles overlap sometimes a little bit?
No. These lucky droplets rarely overlap.
Okay, and
I mean, this I'm telling from the model because model doesn't capture it. But if you go through DNA simulations, which few people in the world can do, they also find that most of the collisions happen with the smallest size particle with the bigger sized particles. Bigger collisions are very rare.
And if you initialize with only monodispersive particles, then will the lucky droplet formation will happen? It means all the particles have the same radius.
Right. But in this model, it won't happen. But in actual, it will happen, but it will take a long time. Like 10 years ago, Shamruddhi was involved in a work where they evolved billions of particles in tens of billions of grid points. And they saw the mass increased by a factor of 15, which means radius increased by less than 4. So in DNS, it takes a long time for those to happen.
Thank you.
Hello, can I ask a question?
Yes, whoever is online, please.
Sam here online. I just wanted to know, for the very small droplets, apart from the fluid motion, is diffusion important?
If you go beyond, let's say, beyond a micrometer, yes, they do have some Brownian fluctuations. But around over a micrometer or so, diffusion might not be as important as the drag. Drag is the most important. But I don't have a quantitative answer on the bridge. Yeah.
Thanks.
Yeah, maybe you already answered, but let me ask again. And so, supposing you have a well-mixed gas of these small particles, and then you have this bigger guy which is kind of doing a random walk or diffusion, right?
Right.
Then one can predict how much it will, how it will grow. Is that what you call the kinetic?
No. It's not even that complicated. It's more simplified. We assume uniform.
Yeah.
We don't care about the velocity of these big ones. We say it's uniformly seeing all the small droplets, and the numbers scales inversely with the number of particles we put in.
Okay, but I mean, if you just think of like, roughly, it looks like your big particle should do some random walk.
Right.
And then it should be possible to predict how it grows. I mean,
we are yet to check that, but this estimate that I showed, it's even rougher than that. Like, we didn't consider the random work. We are just.
And it agrees with the simulations, is it?
No, not qualitatively, but quantitatively, yes. You'd expect with Stokes number, it goes down, and it does go down, but not the exact scaling does not follow. But the one that you're mentioning with Brownian work, we haven't checked yet.
When the bigger droplets have eaten up the smaller droplets, that picture you showed, if you started particles, big droplets from that initial condition, is still the growth rate trends the same for as you're changing the size, or did you only test uniform?
That's a different problem, right? Because when the big droplets have eaten, so we start big droplets with something like this of an initial condition. Now, if you start from this is in the saturation range of the growth rate. This is somewhere here. There is not much small droplets to eat anymore. So they will exponentially saturate to some value.
But like in some steady state case, wouldn't you expect the right thing, the right diagram to be the realistic?
At long time limit, I would say there is no small droplets, because that's what we see in the rain as well, that once a cloud rains, almost all the liquid water content is gone. So the lucky droplets will eat up almost all of the small droplets.
There is no further questions? These lucky droplets can't disintegrate.
They can ideally. They can evaporate if they don't grow fast enough.
Okay, so
that's not in the model. Yeah.
Okay.
No.
Thank you, Rajarshi.
Okay.